Ever pondered about the movement of liquids through a permeable medium? Brace yourself for an intriguing journey through this process, based on a principle called Darcy's Law. This principle, christened after the eminent French engineer and scientist Henry Darcy, paints a detailed picture of fluid dynamics in porous substances. Darcy, a stalwart in the field of hydraulics, developed this law grounded by experimental observations of water flow through sand beds. Now, to help you visualize this more clearly, let's introduce a model of a permeable medium. Watch closely as we exhibit the flow of liquid through it. You're about to get a first-hand experience of Darcy's Law in action. Plunging headfirst into the central tenet of Darcy's Law, it proposes that the fluid flow rate through a porous medium is directly linked to the pressure gradient in the fluid and inversely linked to the fluid viscosity. To better comprehend this, let's take a look at a model demonstrating these principles. This model will visually illustrate how the pressure gradient and fluid viscosity affect the flow rate. Understanding this is crucial in our grasp of how groundwater traverses through various geological formations. Imagine a sponge. Its ability to let water flow through it can differ extremely. This variability can be compared to the permeability of a rock formation. The water flow can either be smooth, laminar, akin to the steady absorption of water by a sponge, or it be chaotic and irregular, turbulent, like water being unpredictably released from a soaked sponge, depending on the size of the gaps within the sponge. Visualize Darcy's Law with this formula. Q equals negative K times the change in pressure, divided by the product of fluid viscosity and length. This mathematical representation, appearing now on your screen, is the cornerstone for predicting groundwater movement in different geological conditions. The negative sign in the formula, as you can see, indicates that the flow of water from a high-pressure area to a low-pressure area. For Darcy's Law to be accurate and applicable, certain conditions need to be met. These conditions imply the flow to be laminar, the nature water and soil being incompressible, the soil being saturated to its maximum capacity, the liquid flow being steady, and the testing temperature assumed to be 27 degrees Celsius. We begin to investigate Darcy's Law as we see it shedding light on the movement of groundwaters in diverse geological landscapes. Picture this. Without a pressure gradient stretching over a particular distance, the flow grinds to a halt, creating what we call a hydrostatic condition. Now envision a contrasting scenario. A pressure gradient is now in place. This prompts the fluid to start flowing from a region bearing higher pressure to one with lower pressure. To bring this concept to life, let's take a look at a model of the flow. And just to highlight, the strength of the pressure alteration is a key influencer in dictating the speed of discharge. In summary, Darcy's Law is a pivotal principle in geology that illustrates how fluids navigate through porous rock formations. You'll see an on-screen graphic now, giving a visual representation of fluid moving through a porous object. The elements of this law, fluid flow rate, pressure gradient, and fluid viscosity, offer profound insights into groundwater behavior under different geological circumstances. So, the next time you see water meandering through the layers of rock, remember that it's Darcy's Law you see in action. Delve into some tangible examples of geological phenomena where Darcy's Law is at work. Our first example unravels the mystery of groundwater movement through soil. Have you ever wondered, after a heavy rain, how water seeps into the earth? This fascinating process is an exemplary instance of Darcy's Law in action. The water, driven by gravity, makes its way through the permeable soil layers. Our next example showcases how groundwater courses through rocks. Observing nature, we see water weaving its way through crevices and gaps in rocks, another exquisite demonstration of Darcy's Law. Understanding these instances is a cornerstone for geological and environmental studies. It supports predicting the journey of pollutants in groundwater and aids in efficient water resources management. These real-world examples clearly illustrate how Darcy's Law unveils the course of water in our environment, cementing its invaluable role in the domains of hydrogeology and environmental science. Now let's visualize Darcy's Law with a sketch. Picture this. You're standing on the edge of a cliff, staring into the heart of the earth revealed in a cross-section below you. The water is ever moving, flowing like a river through the various strata of rock, directed by the invisible force of gravity. This process, the flow of water within the earth, is embodiment of Darcy's law. To truly understand mechanics of Darcy's law, we are going to bring this scene to life with a sketch. So, ready your pencil, it's time to draw. Start with the cross-section of the earth, highlighting the diverse layers of rock. Proceed in arrows that denote the direction of the water flow. The size of the arrows should symbolize the velocity of the water. The bigger the arrow, the swifter the flow. The smaller the arrow, the slower the pace. Remember, the flow is determined by the rock layer's permeability and the gradient. Ergo, layers with higher permeability and a steeper gradient will feature larger arrows, signifying a speedy flow. This sketch, uncomplicated as it appears, encapsulates the very soul of Darcy's law. It illustrates how water traverses through different geological layers by gravity. It's a vital tool to comprehend the science of groundwater flow, the distribution of pollutants, and the management of water resources in a geological context. So sketch, absorb, and marvel at the elegant simplicity of Darcy's law.
Does Darcy's law always hold true? This intriguing query paves our way into the fascinating realm of geological applications. Although Darcy's law has certain limitations, it's a fundamental tool in the field of hydrogeology and petroleum geology. It is indispensable when it comes to understanding groundwater flow or analyzing oil reservoirs. First, it's fundamental to grasp Darcy's law within its geological context. In its simplest form, it elucidates the journey of fluids through porous geological materials. Like this, consider how groundwater seamlessly navigates through an aquifer. This is Darcy's law in action. It provides us with an in-depth geological insight into how water or oil intricately courses through the microscopic interstices within rock formations or sediment layers. Specifically, it plays a pivotal role in our understanding of groundwater flow systems and oil reservoir dynamics. Darcy's law is a geological marvel, especially when it comes to understanding subterranean fluid dynamics, such as groundwater flow and oil reservoirs. Imagine the underground world of fine-grained sediments. Water or oil is guided through small spaces known as interstices. This is Darcy's law at work, maintaining a smooth and orderly flow, akin to a slow-moving river. The application of Darcy's law isn't limited to sediments. It also explains the complex fluid dynamics in coarse-grained sediments, though this area proves to be more intricate. In geological formations such as sand, gravel, and other coarse-grained sediments, the larger interstices or spaces between the grains play a significant role in how fluids flow. This is where Darcy's law comes in. Originally devised to understand the flow of water through sand filters, it is applied in various geological scenarios ranging from groundwater flow to oil reservoir studies. Just like a crowd at a rock concert can be erratic, the fluid can become chaotic in these large spaces, resulting in what we call turbulent flow. When this occurs, Darcy's is no longer applicable. However, determining when a flow becomes turbulent from being laminar or smooth is a challenge in itself. It's here that the Reynolds number, a dimensionless index, becomes integral. It allows geologists to predict flow patterns. A Reynolds number below 2,000 indicates laminar flow, while one above 4,000 indicates turbulent flow. Interestingly, in certain geological formations, fluid flow remains laminar even at Reynolds numbers less than 1. So, Darcy's law and Reynolds number, while not hard and fast rules, are critical tools in our geological toolkit for fluid dynamics in various sediment structures. Darcy's law is a crucial principle in geology, providing key insights into groundwater flow and oil reservoir dynamics. It postulates that the hydraulic conductivity, a significant factor in determining how water travels through different mediums, is a constant for each medium. However, in practical geological scenarios such as oil reservoirs or underground aquifers, the truth can be more complex. The hydraulic conductivity can be by the fluid's dynamic viscosity, which can fluctuate based on the flow rate and temperature. Thus, Darcy's law's applications in geology aren't always straightforward, but they provide a fundamental starting point for understanding fluid dynamics in natural underground reservoirs. Despite these limitations, Darcy's law is a cornerstone in the fields of geology and hydrology. It's used to model fluid flow through different geological structures, shedding light on the complexities of water movement through aquifers. Moreover, Darcy's law facilitates the analysis of oil, water, and gas flow through petroleum reservoirs. It's not just a tool but a foundation stone in our understanding of how fluids traverse intricate geological terrains, including the massive underground vaults of oil reservoirs and the labyrinthine networks of groundwater flow. In conclusion, despite its limitations, Darcy's law remains a cornerstone principle in the field of hydrogeology. This law, when leveraged adeptly, can furnish exceptional insights into the fascinating world of groundwater flow and oil reservoirs. It may not always be universally applicable, but it is a vital tool in comprehending the geological aspects of fluid dynamics.